Welcome to Daily Papers, the podcast where we break down cutting-edge research into bite-sized conversations. Today, we're diving into the world of medical AI and a paper that sounds like it's straight out of a sci-fi thriller.
It really does. Imagine an AI designed to help doctors spot cancer on a patient's biopsy slide. It's incredibly accurate and could save lives. Now imagine a hacker adding a nearly invisible layer of static to that image. And suddenly, the AI is completely fooled. It looks at a cancerous tissue sample and confidently declares it healthy.
That's the terrifying scenario explored in a new paper from researchers at UCLA titled Universal and Transferable Attacks on Pathology Foundation Models. They've basically created a blueprint for how to trick these advanced medical AIs. But, and this is the important part, they're doing it to show us how to build stronger defenses.
Exactly. So let's set the scene. We're talking about a field called digital pathology. Instead of a pathologist squinting through a microscope, a high-resolution digital scanner creates an image of a tissue sample, and powerful AI models can analyze it. These aren't just any AI models, they're what we call foundation models.
Right, and a foundation model is like an AI that's gone to medical school. It's been pre-trained on millions and millions of medical images, so it has a really broad, general understanding of what healthy and diseased tissues look like. Then it can apply that knowledge to specific tasks, like identifying a particular type of cancer.
They're incredibly powerful, but the paper points out that this also creates a centralized vulnerability. If you can find a weakness in the foundation model, you can disrupt all the different tasks it's used for. And that's where something called an adversarial attack comes in.
So, what exactly is an adversarial attack? For anyone not familiar, it's a bit like a magic trick for a computer. An attacker makes tiny, deliberate changes to an input, in this case a pathology image, that are usually completely unnoticeable to a human. But to the AI, these changes are profound.
It's like adding a carefully designed invisible pattern of noise over the top of the image. It's not just random static. Every pixel in that noise pattern is calculated to cause maximum confusion for the AI. To you and me, the original image and the attacked image look identical. But to the AI, a picture of a cat might suddenly look like a picture of a car. Or in this case, a cancerous tissue sample looks benign.
And the specific attack these researchers created is called UTAP, which stands for Universal and Transferable Adversarial Perturbations. The name sounds technical, but the two key words here are universal and transferable. Let's break those down.
Let's start with universal. Most adversarial attacks are custom-made. You need to design a specific noise pattern for a specific image to fool the AI. But the UTAP attack is universal. This means the researchers created a single, one-size-fits-all noise pattern that can be slapped onto any pathology image and still fool the AI.
That's a huge deal. It's the difference between needing to be a master lockpicker who studies each lock individually versus having a single master key that opens almost every door in the building, no matter the lock.
And it gets even more concerning with the second word, transferable. The researchers trained their attack on one specific foundation model, but they found that the same attack also worked on a whole range of other, different pathology models, even models they'd never seen before and had no access to. This is what's called a black box attack.
So, to extend the analogy, that master key doesn't just work on one brand of locks. It works on completely different brands of locks that the keymaker has never even studied. An attacker wouldn't need access to a company's proprietary FDA-approved AI model to compromise it. They could just develop this attack on an open-source model and know it will likely work on the protected one.
So how does it actually work? What's so special about this noise pattern? The paper shows that it's more sophisticated than just tricking the AI into a wrong answer. It fundamentally breaks the AI's ability to understand the image in the first place.
The paper describes it as causing the feature representation to collapse. A good way to think about it is this. Normally, an AI looks at thousands of images and learns to sort them into neat, well-defined clusters in its mind. You have a cluster for healthy colon tissue, a cluster for adipose tissue, a cluster for cancerous cells. It knows what makes each one distinct. But when an image is hit with the UTAP attack, it's like a gust of wind that blows all those neat clusters into one big, messy, chaotic pile. The AI can no longer tell the difference between the categories. Its internal understanding just collapses. And the results were pretty shocking. In their tests, AI models that were over 97% accurate saw their performance plummet, sometimes to as low as 12% accuracy.
This obviously has massive implications for patient safety, but the goal here isn't to scare everyone away from AI in medicine. The researchers are acting as ethical hackers. They're finding the vulnerabilities so that we can fix them.
That's the most important takeaway. This isn't a doomsday paper, it's a roadmap for building better, more secure AI. Now that we know this kind of attack is possible, we can start to defend against it. The researchers suggest something called adversarial training,
Which is basically like giving the AI a vaccine. During its training phase, you show it these attacked images alongside the normal ones. You teach it, hey, this is what a malicious attack looks like. Learn to recognize it and ignore the noise. By training on these tough examples, the AI becomes more robust and resilient against future attacks.
So, in a way, the UTAP attack they designed isn't just a weapon, it's also the perfect training tool to build a stronger defense. The paper provides a clear benchmark. From now on, anyone developing a new pathology foundation model can test it against UTAP to see how secure it is.
So to sum it up, these incredibly powerful AI models that are revolutionizing medical diagnoses have a critical, hidden vulnerability. Researchers have found a kind of master key attack that can fool a wide variety of these models, even without direct access.
But by revealing this weakness, they've given the entire field the tools and the motivation to build much safer and more reliable systems. It's a reminder that as we deploy AI in high-stakes areas like healthcare, rigorous security testing isn't just a good idea, it's absolutely essential. This kind of work is what will ultimately make AI in medicine truly trustworthy.